Well, good afternoon, grade 11s. And listen, let me apologize that I didn't post this earlier. Last night, my cable internet went down in our whole area, just as I was about to start recording your lesson, actually, and it was out from 7 p.m. till when I went to bed. I kept checking, and it just never came back. So anyway, normally I will post this earlier for you, and I apologize for that. But all right, so let's get right to it. Okay, there was a couple of questions from the homework I just wanted to go over with you. And so here you can see question number 11. I forget what page it's on, but anyway, this question about Earth's radius and so on. Okay, here's the deal. When you're doing a question like the one you see on the board right now, what you have to do is just remember the formula that you're using. So the formula that you're using is just the average speed equals the total distance divided by the time, okay? Now there is a little niggle in this question, if that's a word, okay? What you have to do is find the distance by looking at the circumference of the orbital path. So this jet is circling the Earth at faster than the speed of sound, by the way. The speed of sound is around 1,300 kilometers per hour, so it's actually traveling faster than sound. And how much time would it take to orbit the Earth once is the question. Now, a couple of things, you know, some of you were mentioning in the homework, they say that the radius of Earth is 6.5 times 10 to the 3. You'll notice how the textbook absolutely loves scientific notation, times 10 to the everything for all the answers. That's 6,500 kilometers. You don't have to convert it to meters because pay careful attention to the units. Here, up there, the distance, or sorry, the speed velocity is given in, or speed, sorry, is given in kilometers per hour. And the distance is given in kilometers. And so you can just leave it, and when you do the math, the answer will be in hours, okay? So we can leave the units as they are, kilometers per hour and kilometers, and then when we find the time, it'll be in hours, of course, because of the units that you see in the question. Okay, now, a couple of people mentioned, like, wouldn't this guy be driving across the Earth or whatever, because if your path is equal to the radius of Earth, okay, 6,500 is actually not exactly the radius of the Earth. I guess we'll call it the radius of this orbit, the supersonic jet, but that's actually a little bit too high, 100 kilometers or so. Jets don't fly that high, you'd be in outer space at that height. And so, like, look, I just tell students, listen, if you want to add 10 kilometers to it, like let's say you made it 6510, because jets do fly at an altitude of around 10 kilometers above Earth's surface. You'll find that it doesn't make any difference at all in the first 3 digits of the answer. In other words, it's not a significant enough change to worry about it. So whether it's 6,500 or 6,510 or whatever you want to make it, you know, 6,400 and change, you know, whatever, wherever it is, it wouldn't really be a big enough difference for us to get a difference in the time. Okay. Anyway, go ahead and use the formula, and I told students as well today that you need to be able to rearrange these equations and solve for the unknown variable backwards and forwards in grade 11. You've got to be good at algebra in this course. This one's pretty easy. All you have to do is cross multiply, solve for time. Time equals distance over speed. So now we plug in the circumference of the path divided by 1,600, and we get 26 hours. Okay, so that's how you do question number 11. Now, I want to draw your attention to another question number 11, okay? This one came up in the homework as well, and a bunch of the students didn't do it today, and I want to make sure we go over this. You can see I've already done it. I've checked it all off. We've gone over it with the students in cohort B today, so let me do that for you. So here's the deal. Let's take this one at a time. We have a jet that is traveling at a velocity, pardon me, of, it says uniform motion. That's a uniform velocity is what they should have said. But anyway, that's 930 meters per second, which is approximately 2.7 times the speed of sound, because I know you care about that kind of detail. Okay. Now at time 0, it passes a mountaintop, which is used as a reference point, which means in regular language that the position equals 0 when the time equals 0. So we'll treat the mountain as our reference. That means that's a position of 0. Okay. Now, it says construct a table showing the plane's position relative to the mountaintop at the end of each second for a 12-second period. All right, so that's what I did here. So you will see that table right here, this beautiful looking table. I didn't do the whole 12 seconds, but you get the idea. What we're basically doing is using this formula here, that the position will equal velocity times time, okay? We start at position 0, at time 0. Here you can see that in the first entry in the table. After 1 second, the plane has traveled 930 meters. Because after all, it's traveling at 930 meters in every second, right? Now, a second after that, it's gone twice as far, 1,860 meters. Then 2790, okay? Then 3720, and so on. Now you can keep going until you get up to 12, okay? Now we actually used a computer software to plot this data. I'm not gonna bother with that now. I'll just draw a sketch for you here. If you were to plot that on a position time graph, so this is the next question, you get a straight line, okay? Now, so what we've done is we've done question A, we've done question B, okay? Now it says question C, find the slope of with two different segments. So you know already that slope is rise over run. So I could do this, rise and the run. I could find slope. I could do that somewhere else. Two different segments, right? And I could do the run here and the rise here. And if it's a perfectly straight line, it really doesn't matter where you find the slope, right? You can use any line segment you want, anywhere on the line. You'll always get the same answer. And by the way, the slope will equal, pardon me, you'll find that the slope, no matter what you do, the slope equals 930. And it has units in meters per second, because when you divide meters, the rise is in meters, the run is in seconds because it's time. When you divide them, you get meters per second. That's not a coincidence. And we recognize that number. That number is the velocity that was given in the question. So what did we just prove here? We just proved that the slope on a position time graph is equals to the velocity, right? Which you know already, okay? So that's all they're doing there. Now, it says, is the slope constant? The answer is yes. What does it represent? The answer is the velocity, okay? Now let's look at question D. Plot a velocity time graph. Now this one is a little bit different, okay? So we're gonna talk about velocity time graphs in today's lesson. And then it says, in question E, calculate the total area under the line. All right, so let's do that. In fact, I've got the velocity time graph right here. See, this plane all the time is traveling at a uniform velocity. And that means that it holds a velocity of 930 the entire time. So it's constant. Now, a constant thing that never changes looks like a horizontal line that is a constant velocity on a velocity time graph, right? So this is not a position time graph, it's a velocity time graph. And now it says, what is the area under the line? Well, that's this region in here is the area under the line. And why would they bother asking us for the area? Well, first let's just do it and I'll show you why they bother in a second. Look, to find the area underneath this line, all we're gonna do is go length times width. So here I did it for you here. The area of a box is length times width. So that's 930 times 12. So here we see that the box has a width of 12 and a length of 930, or whatever you want to call the length of the width. It doesn't really matter which order you do it in. That gives us 11,160 meters. Okay, so that's the area of that box. I just showed here how the students, the units work out. It gives you meters. That's not a coincidence. And by the way, this happens to equal the total displacement. Okay. So in other words, it equals the last entry in your chart, okay, where the plane is after 12 seconds. That's the total displacement of the plane. See, that's not a coincidence. So what they're trying to establish for you here is that the area underneath a line is equal to the displacement of the object. All right, so now we've done the homework questions that I wanted to cover. Let's talk about today's lesson, velocity time graphs. Oh, actually, before we do that, just a brief little note here for you. Okay, So we talked about, I think we talked about tangent lines and instantaneous rate of change and average rate of change. I think we talked about that. Like some people were asking me about this. Actually, you know what? We need to go over this. So let me go over it again. I'm going to erase all this. It's getting very messy. So let me erase all of everything you see here. And let's take a look at this graph. Okay. And we'll take up some of the questions together. All right. Oh, it takes a long time to erase some of this stuff. There's a few more lines. I'll just get rid of those here. Okay. So here you go. Here's your position time graph. Okay. Now remember, what you need to know about this is that the slope is equal to the velocity. Okay. So that's important. Now, if you have a curved line, that means you have a changing slope. So here in section A and section B, here these lines are straight, which means they don't change. So in this case, and in this case, it's a uniform velocity. In section A, the velocity equals 0, okay? In section B, the velocity is the slope of that line, so the rise is 2 and the run is 1. So this, or sorry, the rise is 4 and the run is 1. So this is 4 meters per second. That's the velocity in section B. Well, what's happening in section C? Okay, that's this section here, and I'm just going to highlight it for you with this little highlighter. What's happening there? Well, the line is curved. So the definition of a curve is a changing slope. The slope is changing, and therefore we have acceleration. Right? A line with a changing slope is a curve, and a changing slope, because the slope equals velocity. If the velocity is changing, that means you have acceleration. Okay. Now here we find that the line is curved in 2 regions, region C and region D. Okay, so let me highlight region D in the different squiggly here. In this region too, it's also curved in that section. And so that is also an example of acceleration. Okay, now in section E, E and F, here we have a straight line segment. And in these 2 sections, we have, a velocity of 0 in section E. And here, if we do rise over run in section F, we get 12 over 1, negative 12 over 1, pardon me. So here, the velocity is negative 12 meters per second. So that's just slope of the line, right? So how do we do slope when it's a curved line? Well, I don't think I got to explain this very well yesterday. So let me get to it right now. And in order to do that, I'm going to pull up okay. No, I don't want that. Okay, just give me a moment. I'm just organizing myself. Okay, so I'm just getting the thing I want to get ready for you. All right, here we go. Okay, so I'm going to drag this over onto your screen so you can see it. Okay, now if you take a look at this graph, here I have a curve. Now the curve is represented by the red line. I don't know if it'll let me draw on this, so I'll try it. Yeah, okay. So the curve is represented by this red line. Now you can see that here like that. I'll just highlight it there for a second. That red line, let's say that is our position time graph. Now this blue line is called a tangent line. Okay, so the blue line is a tangent line. Now I can move the tangent line around, okay? Now, what is the tangent line doing for us? Well, it's telling us how steep the red line is at a given point. So let's say we look at here, this is the 4-second mark. Now, if what I do is I drag this over to the 4-second mark here, and then what I'm going to do again is I'm going to zoom in. I'm going to zoom in. Okay, so there's my, I'm a little off the 4-second mark here, but I'm zooming in. And if you look, when you zoom in to it, you can really kind of see that the red line and the blue line are becoming more and more of a match in slope, right? So here's the definition of a tangent line. It's a line that touches a curve in one spot, but it matches the slope of that curve at that spot, okay? So what it's doing is it's telling us how steep the red curve is at the 4-second mark right now, okay? Now, it might be hard for me to measure the slope on a curve, but the tangent line is a straight line, so I can measure the slope of that tangent, and that will tell me, okay, what the velocity is, okay? So the slope of the blue line will tell me the instantaneous velocity at that point. Why instantaneous? Well, it means at exactly 4 seconds. See, at 5 seconds, which is up here, the red line is now steeper. Okay, so at 4.5 seconds, I'm sorry, I'm seeing the numbers at the bottom now. So at 4.5 seconds, our red line is getting steeper. And so, you know, if I'd have to move my tangent line, so let's see if I can do that. I'll move my tangent line up here. See, at 4.5 seconds, I have a steeper slope. So this curve, we see that the velocity is increasing. The slope is increasing all the time. Now, how do you draw a tangent line if that's your job on a test or something or on a quiz? Well, what you do is take out a ruler, okay? And you could measure it, like draw it like by eye, basically, and then measure the slope after you draw it. And that's what you do, okay? All right, so now that you've seen all this, let's go back to our graph sheet with the questions on it and everything, and let's see if you can answer some of the questions based on what I've said already, okay? Now, here's the questions that you have. All right, so let's go through these questions here for a moment. First of all, what's the total displacement? No problem, we did that in class, beginning point, end point, and then it starts at 0, ends at 0, so the total displacement is 0. Now, what is the displacement between 2 and 7 seconds? Well, we did that also in class. So at 2 seconds, the object is here. At 7 seconds, the object is up here. And so it goes from 4 meters to 12 meters. That is a displacement of 8 meters, okay? And so that's why the answer is 8. Now, distance is a bit tricky. For distance, you have to follow the path, but I did that with you in class, okay? So that's how you get the 40 meters. Now, what about the velocity? Now look at this question here, question D. What is the velocity at, now this is instantaneous velocity at 1.5, 3.5, and 8.5 seconds. The instantaneous velocity, okay? So we're asking you for slope of tangent, okay? At these specific time intervals, not even intervals, at these specific times, what is the velocity, okay? So now we go back to our graph. The first time is 1.5 seconds. Okay, so let me erase some of the noise here. 1.5 seconds. Okay, so 1.5 seconds puts me right here on that straight line, okay? And that's the straight line that you see highlighted by this yellow highlighter, okay? Now that line is straight all the time. Now here's the thing. We just did a question in the homework where we measured the slope of a straight line with different line segments. What you'll find is if it's a straight line, it doesn't matter where you measure the slope, right? So you don't have to draw a tangent line for straight lines. Okay, straight lines, we just measure the slope of the line because it's a uniform slope. So here's what you do. Like, don't Yeah, okay. I'll explain what you do correctly first, and then I'll explain a common mistake that people make. So what I'm going to do is I'm going to pick my beginning points and end points of this line, and I'm going to say, okay, the run is 1, and the rise is 4. Okay, so therefore the slope at 1.5 seconds equals 4 meters per second. That is the slope at that point. Now, it would be exactly the same answer if I had said 1.1, 1.2, 1.3, 1.4, 1.5, all the way up to 2.0, because that's a straight line. That yellow line that I highlighted, straight all the way. So that means it always has a constant slope all the way up. So the answer is anywhere between 1 and 2 seconds. This is your answer. That is your answer, 4 meters per second. Now, what's a common mistake? So don't be the kid that makes this mistake. And I'm going to write this. This is the mistake. Don't do it. Okay, don't do this. They'll take this point here and they'll say the speed or the velocity is equal to, and what they do is they read across here and they say, okay, it's 2, so the rise is 2. But then they say the run is 1.5 because we're at the 1.5 second mark down there. So they go 2 divided by 1.5. No, okay, that's not the slope of that straight line that I highlighted in yellow there. That's incorrect. Don't do that. Okay, that's just not right. So please don't do that. It's a common mistake. I see it all the time. I'm still waiting for a class where the entire class, nobody does that. Okay, so just remember, slope at a moment in time. If it's a straight line, it's easy. Okay, so if I ask you what the slope, what the velocity is or the slope is here, at this spot right here, it's 0. It's also 0 there, 0 there, 0 there, it's 0 everywhere there. Anywhere on this line, any point on this line, the answer is 4. Now, where it gets interesting is at the 3.5 second mark. That's where it gets interesting. The reason why it gets interesting there is because at 3.5 seconds, that puts us right here on this curve. That is the 3.5 second mark. Now, that's a curve. So in order to answer that question, I need to draw a tangent line. Okay, so let me go ahead and draw a tangent line for you. Oh, let me get rid of this. Okay, so I'm going to draw the tangent line for you. I have to do it freehand. Unfortunately, I've tried this before. Let me just try it. Probably not going to work. I've tried the straight line tool. And so let's see if I can see it snaps it, right? Like it's so stupid. Anyway. Okay, so like, I think roughly that's the right slope. I'm trying to match the slope. Okay, now let's see if I can move that. No, it doesn't like me moving it that way. So let me see. All right, there. Actually, that's not too bad. Okay, so that rainbow line that I just drew is a tangent line. Now, all I need to do, the tangent line, it tries to match the slope of the curve at the spot at 3.5 seconds that lands on the curve. And now all I need to do is find the slope of this line, right? Now, the slope of that line, you can make that line as long as you want. In fact, it's nicer to make it across the entire graph. And then you just pick 2 convenient points. I'll pick this one. You pick them that are nice and far apart, okay? Don't pick 2 points that are really close together. That's a mistake. Make them nice and far apart. So I'll pick these 2 points, okay? Actually, maybe I'll extend the line. No, I'll pick those 2 points. That's fine. Okay, so what's my rise and run on my tangent line? Well, my rise is from 8 to negative 5.8, let's say. So I'm going to go V equals negative 5.8 minus 8 at the top. That's my rise. And my run is from 1.5 seconds to 6 seconds. So it's going to be 6 minus 1.5. Now, if I take out my calculator and I go 5.8 negative minus 8 equals, and then I'm going to go divided by bracket 6 minus 1.5. Okay, close the bracket, equals, and I get negative 3.1. Okay, so now you'll notice in the answers, I wrote negative 4. That's not really right, okay? Now maybe my line isn't steep enough. Maybe I could have made it a little steeper, but I think I'm a little off there. So let's change that one to negative 3.2 or something, meters per second for this answer in here. Okay, but yeah, see how I did that? Like, so it's the slope on a curve. Slope on a curve. You have to draw a tangent line, which my rainbow line there is a tangent line. Okay, and then what you do is you find the slope of that tangent line, and that tells me the velocity of the object at an instant at 3.5 seconds. Okay, so that's how you do slope of tangent on a graph like this. Now, by the way, at the 8.5 second mark, just to finish the question, we're here at 8.5 seconds. That's a straight line. So it would be the same answer if I said 8.6 or 8.7 or 8.8 or 8.9 or 8.4, 3, 2, or 1. It doesn't matter what point you pick. It's the same straight line, has a uniform slope. So all you have to do is choose your two endpoints here and here, because this line has a uniform slope, that line there. And that means it doesn't matter where you measure it. You can pick any interval you want to measure it in. Okay, so the instantaneous velocity right there would be just the slope of that straight line, which would be negative 12 over 1, or negative 12 meters per second. All right, position time graphs, there you go. Now, there's one more question for you, and it's question F here. During which intervals is the acceleration 0, positive, or negative? Okay, so we already know that, I'm going to erase a lot of this. Okay, we already know that a changing slope means there's acceleration. And if the line is straight, that means the acceleration is 0 because the velocity is not changing. So at A, B, and this is C over here. At A and B and E and F, so let me highlight those sections. These yellow sections here, the line is not curved. They're all straight lines. So in all of those sections, the acceleration equals 0 for all of these sections, okay? And here also, acceleration equals 0 for F and for E, because the line is straight. That means 0 acceleration. Now, if the line is curved, that's where we have acceleration. Now, I'll give you a little trick. How do you know if it's negative or positive? Well, look, do you know what a smile looks like? Okay. And do you know what a frown looks like? So any line that looks like this, that's a smile. That is a positive acceleration. Any part of that line would be a positive acceleration too. Now, if the line looks like that, that's a negative acceleration. Any part of a frown is also a negative acceleration. So it's easy to remember. A smile is positive and a frown is negative. Okay? So section C, this section here, which I'll use a rainbow, that is part of a frown. It's not the whole frown, but it's part of it, right? So this has a negative A. Right here, negative acceleration. But section D, which I use my squiggly rainbow, this section here, that is part of a smile and it has a positive acceleration. Okay, so there, that takes care of position time graph. And now that we finished that, we have one more type of graph. This won't take as long for me to explain. I explained it in about 10 minutes in class. So I'll do the same with you. So let's take a look at another kind of graph That's called a velocity time graph. So let's go here. All right. Okay, now we're going to look at a completely different kind of graph. So this one's called a velocity time graph, and this is actually a really important kind of graph. So remember that now, forget the position time graph for a second. Okay, just forget about that. Now we're looking at a new kind of graph, and this new kind of graph is called a velocity time graph. Now here's the deal. Obviously the value on the line is the velocity of the object, of course, okay? The change in velocity is just v2 minus v1, it's delta v, right? Now if you look at slope, well, when you do the slope, it's rise over run, where you're going to get delta v over t. But you see, that's the definition of acceleration, because acceleration equals the rate of change in velocity, okay? And so that's equal to the change in velocity divided by time, right? Now that's the slope on a velocity time graph, okay? So now listen, on a position time graph, the slope was equal to velocity. But now on a velocity time graph, the slope is equal to acceleration. So it's a different meaning of slope. Okay, now again, the slope of the tangent would equal the instantaneous acceleration. Oops. The instantaneous acceleration, because slope is acceleration, so slope of tangent again would be instantaneous acceleration. I don't need to explain that again because you know what tangent means now. I just explained it. So now your tangent slope would equal acceleration instead of velocity on this kind of graph. All right, let me erase some of this. And let's start over here. Okay, so here's an example of a velocity time graph. And I'm going to put back some of what I just erased. I'm going to divide this up into sections, A, B, C, D, and E. Okay. Now, what we learned from the jet plane question, one of the first questions I did for you today on this lesson, what we've learned from the jet is that there's another thing that's true about a velocity time graph, okay? So the area under the line actually represents the displacement of the object, okay? That's what the area under the line represents. Now the displacement is negative if the line is below the axis, okay? And so we measure this area above the line, but it would be a negative displacement. Here we can see that I've calculated the areas for you already. And this area here above the line would be a positive displacement, okay? So just remember that the area equals the displacement, okay? Now, by the way, if we don't count negatives, okay, like the total area would be the total displacement. So why don't I write that? The total area equals the total displacement. That makes sense. The total distance would also be the total area, but we wouldn't count these values down here as negative. We would count them as positive numbers. That's to get the total distance, okay? So I'm just going to say the total distance is also equal to the total area, but no negatives. Okay, so keep that in mind. All right, so now that we know slope is equal to acceleration and area equals displacement, now let's look at the questions. So here are some questions for you. It's the same graph, second page. So what's the acceleration during the first 2 seconds? Well, during the first 2 sections is the slope of that line, okay? Now I'm gonna let you measure the slope of that line. I mean, the rise is 3 and the run is 2, so it's gonna be 1.5, okay? I forgot to write the answer there, but anyway. So that's the first 2 seconds. At the 7-second mark is right here. It says, what is the acceleration at the 7-second mark? Well, it's equal to slope. Please don't say it's 0, because that's making that mistake I told you not to make, okay? It's not 0. The answer to this question at the 7-second mark, it would be the same answer here, the same answer here. It's the same answer anywhere on this straight line because a straight line has the same slope everywhere. And so what you're really being asked is to find the slope of that whole line. And that will be the answer at 4, 5, 6, 7, 8, all the way up to 9 seconds. That will be the, the acceleration in that entire interval, okay? So just measure the slope of that line. Now it'd be a negative slope, and that's fine. You can have a negative acceleration. It is a vector, and so you can have a negative number. Now, what is the total displacement for the whole trip? So let's talk about this question. What is the total displacement for the whole trip? Add it up, find the total area, okay? Now, the negatives count as negatives. So it's going to be 3, 3 plus 6 plus 4.5, then plus -2 plus -2. And when you add a negative number, you subtract. So be careful. All right, and then it says, what is the acceleration? Oh, pardon me. What is the total distance covered by the object? So when you're doing the total distance, let me start over here. The total distance, you go 3 plus 6 plus 4.5, but then you go plus, don't do a -2, you just go +2 and +2 again. We don't treat negative displacements as negative when you're finding distances, because the negative sign just has to do with direction. So distance doesn't care about direction. So we treat negatives and positives the same. They're all positives. So that's for distance. Now, what is the average velocity and the average speed? Well, once you've answered question B and C, the average velocity is just the total displacement over time. So that's the area, right, over the time. Now the area including the negatives because it's displacement, right? And the average speed would be the total distance divided by time. And that is the answer, where we count the -2's as positives and we add it all up. So you just go distance over time. And that's how you do the average speed. Okay. Now it says, what is the slope of tangent on the corresponding position time graph at 3, 5, and 7 seconds? I would like to leave this question for tomorrow. So please skip it for now. And then it says, during which time intervals is the acceleration 0, positive, and negative? Okay, so the acceleration is just the slope. So just change this word, change that word to slope. And then you should be able to answer it. I would also like you to skip this question for now. Okay, just skip it for now. We'll do it tomorrow. All right, so that's it for now. That's the lesson for today. Just let me show you in the outline where we are in the homework. So I've now highlighted parts of lesson 3 and 4. So I just gave you a worksheet and we did most of it together. So that takes care of lesson 4 for you. Okay, and on lesson 3, there's various questions on page 28, 30, and 36. So just add that to the homework. So it's not a lot of new homework today. And otherwise, I will see you tomorrow and we will take care of the rest. Notice we have a quiz coming up for you. That's Friday. Okay, for you, that's Friday. Cohort A, that's Friday. Cohort B, we decided we'd do it on Monday, just so I get a chance to review with them in class once before they write it. Okay, but we'll see how it goes. But for you, cohort A, that's on Friday. Now, we are going to move on in the meantime. We're not just going to sit around waiting for you to write the quiz. I'm just trying to give you some time to, absorb the information that we've learned on graphing and stuff. And make sure you can answer the questions. And then I'll show you a little practice quiz, and then we'll do it. Should be easy, okay? But you've got a little bit of work to do before we get there. And that's it. Okay, so that's it for today, guys. Have a great evening. I'm sorry I posted this so late, but enjoy the rest of your day. And I will sign out of this.